Viewers like you make this program possible. Support your local PBS station.
A forest on fire ignites the strength inside a 30-ton solid steel frame.
Our steel has to be very high strength, essentially to absorb the energy that's multiplied by these huge payloads.
The hunt for whales inspires a vital liquid that cools massive brakes.
This oily coat reduces friction, it reduces abrasion, and it reduces heat so that the parts last longer.
And the milk of a tropical tree forms tires taller than 2 men.
The key raw material in our tires is rubber, and lots and lots and lots of it.
Together, they create a truck that moves mountains. Natural resources, critical moments in time, and human ingenuity forged the world's most awe-inspiring machines. From raw to ready. For centuries, humans have searched for new ways to harness and transform raw materials, found in places like this. The Highcroft open pit mine in northern Nevada. Here, beneath the earth, are over 30 million pounds of precious metals. To extract them takes a massive 230-ton, 2-story tall dump truck with a load capacity of 320 tons, heavier than a 787 Dreamliner jet, a giant earth mover. The Komatsu 930E.
To give people a sense of the scale of what we do here, maybe the Gecko is the pickup truck, and the Tyrannosaurus Rex is actually our mining truck. It's just on a scale that's almost unimaginable.
It's an amazing engineering achievement, made possible by 5 unexpected, essential raw ingredients. Chromium, a mirror-like decorative plating, also one of the smoothest surfaces on the planet. Mineral oil, the surprising petroleum product made possible by a 19th century lamp. Latex rubber, an Amazonian tree's natural defense turned into powerful traction. Sulfuric acid, inspired by the reflexes of a frog. It's an electron superhighway, generating massive power. And first, a raw material that's the true source of strength behind the truck's 30-ton frame. Earth movers like this haul up to 640,000 pounds per load. Standing firm under all this weight is a solid steel chassis. The secret ingredient that makes it this strong is coal. 18th century England, and the forests are on fire. For thousands of years, people have been using the wood from England's abundant forests to heat their homes, cook their food, and make metals like iron. They've been chopping down trees and burning the wood to create not coal, but a similar carbon-based fuel, charcoal.
Charcoal is made by burning wood in an atmosphere with little oxygen. Too much oxygen and it turns into ash, rendering it useless. We need just enough oxygen so that we get rid of the impurities, but we keep the carbon.
But the massive need for charcoal is putting an enormous strain on the forests of 18th century Britain. And as the population expands, farmers and ranchers are clearing more and more woods for agriculture and cattle. Forests are disappearing, and wood-based charcoal is becoming increasingly rare and expensive. The world needs a cheap alternative, and iron maker Abraham Darby believes he has the solution. It's another fuel, not made from trees, but mined in the earth. It's plentiful and found everywhere. Coal. But there is a problem. Carbon, found in charcoal, and its potential replacement, coal, is more than just a fuel to separate pure iron metal from rock ore. It's also an essential additive needed to strengthen otherwise soft iron.
If you make things out of pure iron, they're going to be way too soft. Swords will bend, train tracks will sag under their own weight.
Zooming in to over 1 million times magnification, it's easy to see why iron has trouble holding its shape. Its atoms are naturally aligned in neat, organized rows and layers.
When two forces push on different sides and cause the atoms to move by one another, essentially skipping over from one to another, it's how a metal deforms. This is where carbon in coal makes a big difference. Adding carbon to iron changes its crystal structure, and it makes the valleys between atoms deeper so that when one atom moves over to the next, it's more energy for it to overcome.
Unfortunately, raw coal contains more than just carbon. It's packed with impurities, and these added impurities seep in with the carbon, undermine that strengthening process, and make the iron brittle.
One of the main problems with coal is that it contains sulfur. And sulfur in iron forms iron sulfide, which makes it too hard. It in fact makes it brittle. A perfect example of this is the Titanic, where the rivets had too much sulfur, and when it impacted an iceberg, bang, it failed like a glass.
But Darby thinks he has a solution. It's a cooked coal that bakes out the impurities, called coke. And in 1708, he purchases a blast furnace to test his method. Day and night, he and his men labor over a scorching furnace that blazes at 3,500 degrees Fahrenheit. After weeks of grueling work, they succeed and open the door for cheap, coal-strengthened iron.
Cheap iron changed everything. Before, it was too expensive to build an iron bridge, but afterwards, it became affordable.
Now, with a clean, plentiful, coal-based fuel source, iron production is ready for Henry Bessemer. In 1856, he perfects a revolutionary iron-making process that simultaneously melts the iron, removes impurities, and precisely adds the correct amount of carbon, creating an alloy that's both strong and flexible. An alloy we now call steel, the perfect metal for the frame of the 930E. Today, to keep up with growing yearly demands, steel companies worldwide produce as much as 1.5 billion metric tons of steel for industrial needs like mining trucks. The molten steel is first poured into a casting machine that shapes and cools it. It emerges in one continuous piece. Then, a nearly 18,000-degree argon torch cuts the thick metal into uniform, rectangular chunks. The result is a red-hot slab. Next, hot strip mills reduce these massive slabs into various thicknesses. Workers cut the finished steel into customer-defined, individual-sized parts. Once the parts have been fabricated, the next crucial step is bringing them together at the assembly plant. The first stage, building the 30-ton frame.
The manufacturing process at Peoria's manufacturing operations begins with the backbone of the truck. We receive our materials in, which may be plate steel or castings, and we begin to go through the process of assembling and welding up our frame.
The steel they're using is up to 2 inches thick. Creating welds as strong as the coal-strengthened steel itself requires a submerged arc welder. a device capable of generating a 14,000-degree electrical arc that melts the sheets together.
Submerged arc welding, or subarc welding, is when you take the tip of the welding gun and bury it in a media called flux. That flux does two things. It keeps the weld warm, and it also protects it from gases that will put impurities into the weld. What you're left with is a weld that's stronger than both of the pieces that you just put together.
But using the sub-arc method on such a large frame isn't easy. For the flux to stay in place, the surface must be flat and level. This presents a huge challenge on this monster frame, which at this point weighs a whopping 30 tons. Steel perfecter and engineer Henry Bessemer would have never dreamed of this solution. It's a giant rotisserie called the spinner. Welders can work on each joint in a flat position by rotating the steel frame up to 360 degrees. As they finish one side, they simply spin the 60,000-pound frame to the next position.
The frame is so heavy that if you held it on both sides, it would bend under its own weight if it was pure iron. A few atomic percent of carbon from the coal makes it strong enough to hold all the weight it needs to.
But even steel strengthened by coal is only as strong as its weakest weld. Making sure the welding team's done their job right, at the next station, each and every weld is given a thorough inspection, deep inside the joint.
The real-world stakes of welding are enormous. If it's not done right, megastructures can collapse. People can lose their lives.
And what we're doing is an ultrasonic test. It's a sound-induced test. It sends sound waves, very high-pitched sound waves, into the material.
This handheld transducer produces sound waves at such a high frequency they can't travel through air. In order to penetrate the surface of the steel, a technician applies a special couplant gel to form an airtight seal.
It's similar to an ultrasound when you're in pregnancy, sort of the same thing. Now what it does is, because the sound won't travel through air, it makes a solid connection between the transducer and the part.
The ultrasonic waves show a constant wavelength through the steel. Any gap in the sound means a break in the weld. The break will show as a blip on the monitor, alerting the inspector the weld must be redone.
We have a bunch of good welders here. They do a pretty good job, but it's not an exact science.
It's a crucial step. Any minor gap in the weld now could result in major challenges at the mine site, leading to lost time and lost money.
We're looking for anything in the weld that could compromise its integrity and cause anything at all to happen. And it's best to find this early as opposed to later on.
The last step in frame construction is finishing. To protect the surface from corrosion and prepare it for painting, the steel surface is cleaned and smoothed with a unique process, blasting. The coal-strengthened steel used on the frame is so hard, the only thing strong enough to blast it is more coal-strengthened steel. In this booth, the secret ingredients are tiny, sharp-edged steel pellets. They bombard the frame like shrapnel from a grenade, removing excess weld material, or slag, and any other imperfections. After a quick coat of primer, the nearly two-story steel frame is complete, a towering foundation made possible by entrepreneurs Abraham Darby and Henry Bessemer. Ready to shoulder 320 tons, all thanks to a lump of coal. The steel frame has to move, and to do it, it takes no ordinary tires. Earth movers support 320-ton loads across rough, uneven ground at the mine site. To get the job done, these trucks need 6 specially designed, heavy-duty, off-road tires. Each one weighs almost 1,000 pounds, stands 12 feet tall, and is made almost entirely of material that would have gone untapped if it weren't for one man's obsession. It's rubber. 1834, New York City. 34-year-old hardware store merchant Charles Goodyear is bankrupt. He's obsessed with a new material that most people believe is useless. He believes it's a breakthrough idea that will make his fortune. An all-natural product derived from South American trees, rubber. First discovered in the Amazon rainforest of Brazil, natural rubber begins its life as latex, a milky substance inside of plants, including the para tree. It's not the same as sap, a liquid that trees use to move nutrients in water. Instead, latex's amazing ability to stiffen when it comes into contact with air makes it an ideal natural defense against plant-eating insects, and an intriguing natural ingredient for making flexible and durable products.
The fantastic part of rubber is that unlike metal, where there's a whole bunch of atoms in lines and it's rigid, rubber has very long chains of atoms that are weakly bound together, and they can move past each other. It enables it to be stretched to very long distances, and then when released, it snaps back.
But as Goodyear knows, rubber has some major drawbacks. It naturally breaks down in the heat. The rubber products that flood the market in the early 1830s quickly deteriorate when temperatures rise in the summer.
Rubber is composed of long spaghetti-like chains. Each one of these chains is held together by a protein bond that's weak. These weak bonds are broken when the temperature is elevated, turning the rubber into a smelly goo.
Charles Goodyear is working on a solution. He thinks the answer is adding sulfur, but serendipity provides the real answer. While visiting a local shop, attempting to sell his imperfect wares, rubber overshoes, an accident happens. He clumsily drops his rubber sulfur mix on a wood-burning stove. There's a miraculous transformation. The soft, pliable material turns to charred, leathery rubber right before his eyes. Goodyear has stumbled onto a process called vulcanization.
By adding sulfur and heat, he created much stronger, more permanent bonds in the rubber between the long spaghetti-like molecules. It was like tying it together with wire rather than string, and when you pulled it apart, it would snap back together.
At the Michelin factory in Lexington, South Carolina, this tough, vulcanized latex rubber makes up as much as 40% of a finished off-road mining tire.
There's over 135 components in each earthmover tire, and putting those together using the quality specifications as well as the technology that it takes to put that tire together is really quite impressive when you look at the size.
There are 3 critical steps: mixing, layering, and molding. In mixing, natural rubber blocks are blended with proprietary additives to create specialized, sometimes top-secret rubber compounds. These formulas are closely guarded secrets. The recipes are specifically crafted to address issues like durability, hardness, and moldability.
It's not just one rubber, it's many different types of rubber compounds that are in those tires. And all of those compounds are engineered to a very specific property.
While Michelin won't reveal the specific recipe for their off-road tires, the most critical and visible additive is carbon black, a byproduct of oil. It gives rubber tires their signature black color, while providing additional durability, up to 100 times more resistant to wear than plain rubber.
Instead of connecting the molecules together, carbon black fills the spaces between them, like concrete between rebar. It makes it stronger and increases the life of the tire.
To multiply rubber's tough, elastic properties, the next important step is layering. Various rubber compound sheets are fed onto a spinning drum. By mixing and matching compounds with different properties in a single tire, the factory can fine-tune the characteristics of the finished product, providing more grip or durability. Once the end of each sheet lines up correctly, workers apply sealant to glue each layer together. The last step is molding. Each layered tire enters a heated mold. The heat softens the rubber, allowing the tire to form into the shape of the mold. This creates a tread pattern on the tire's surface. Tread patterns vary depending on the use of the tire.
The tread and the sculpture are a very important part of its performance. The grooves, in fact, we have them in several different directions. This helps to provide traction, not only as we're going forward or we're braking, but also as we're moving from left to right and in cornering.
For an earth mover of this size, the tread will increase the natural grip of the latex rubber, while distributing heat to keep the tires cool. Compared to the size of an average car tire, the end result is difficult to comprehend.
The tires that we would normally put on trucks have gone from roughly 6.5 or 7 feet in diameter to 12 feet in diameter. That gives you some idea how much the product in size has just grown in the last 25 years or so.
The newly molded off-road tires are prepared for nearly anything, due in large part to the tenacity of Charles Goodyear and a unique milky fluid found in a tropical tree. But massive tires are only as good as the suspension that supports them. Giant earth movers handle 320 tons of weight while managing every rock in the road. This epic feat takes super strong shock-absorbing wheel struts. At the heart of this rock-solid suspension is a 5-foot-long, smooth steel piston, cushioning blow after blow while staying perfectly smooth. The best surface material for these pistons is an element better known for beauty: chromium. 1797. French chemist Nicolas Louis Vauquelin receives a sample of a rare mineral from the Ural Mountains bordering Siberia called crocoite. He knows it contains lead, but there's one other mystery ingredient. It's the source of its amazing red-orange color. He names the new element chromium after the Greek word chroma, or color. It's an incredible chameleon of color, and it goes on to become a popular ingredient as the base of yellow, green, orange, and red paint. Less than a decade later, and scientists are experimenting with a new form of surface coating. Not paint, but electroplating.
Electroplating is done by taking two metals and putting them into a chemical bath. One is positively charged and one is negatively charged, and a current is run through it. Metal ions come off the positive side, move through the liquid, and attach onto the negatively charged metal. They atomically bond with it. This is not like painting where it's just on the top. They become one with the base metal.
Over the next 50 years, metallurgists test electroplating on countless metals. They uncover how each metal requires its own unique and sometimes complicated formula of chemicals and currents. Many researchers are fascinated with the potential of chromium and the unusual way it corrodes.
All metals corrode, some more than others, but chromium is very special. It forms chromium oxide, which protects the underlying steel. It's the key to making steel corrosion resistant.
Then, in 1925, American chemist Colin G. Fink cracks the code for chromium, developing the first commercially viable chromium electroplating method. His first success? Chrome-plated doorknobs. With its unique resistance to scratching, corrosion, and its beautiful shine, Fink opens the door for everything chrome, from car bumpers to massive earth mover suspension pistons. At Indian Head Plating in Chippewa Falls, Wisconsin, they use the power of chromium to turn 5-foot-long steel rods into smooth-as-glass, chrome-plated suspension pistons. There are 4 key steps: grinding, plating, assembly, and testing. To begin grinding, technicians take the unplated, shiny steel pistons and remove micrometers of steel off the surface. This creates the perfect platform for the upcoming plating and compensates for the added thickness of the chrome, ensuring the finished part will fit perfectly.
Chromium has great wearability, which means it doesn't scratch or deform over time. This is important when you need to have a perfect fit between parts.
So right now I have to bring this down to a specific size. In this situation we have a 3 thousandths tolerance. So right now I have 4 thousandths to go after I measured it. Your hair is approximately 3 thousandths thick. So I have to bring this down to 0.004. Right now I'm plunge grinding, just going straight down onto the part. And I'll zero it. That's my new zero now. I'm going to make the rest of the part look similar to that.
Next, it's electroplating. To begin, a technician lowers each 1.5-ton unplated steel piston into a chemical bath of sulfuric acid and chromium flakes. These flakes are a combination of chromium and oxygen, known as chromic oxide. In this flake form, the chromic oxide has a reddish-brown color.
The bath has to maintain about 138 degrees to be an accurate plating temperature.
A metal bar connected to the piston gives it a negative charge. Lead rods surrounding the piston carry a positive charge to the chromium particles in the bath.
Sulfuric acid breaks down the red flakes, pulling out the chromium ions. Those ions move through the solution and then attach to the piston, leaving a shiny, metallic surface.
Though the piston needs a thick enough layer of chromium to protect it from wear. If the layer gets too thick, the part won't fit in its airtight container. To produce the precise thickness, technicians need to stop the process at just the right moment. After 3 hours, the technician removes the piston from the bath. The chrome layer is now 4 thousandths of an inch thick.
The tolerances that we have to maintain are very critical, both in the chrome thickness that we apply and the overall diameter of the part.
Back at the assembly plant, these now chrome-plated, shock-absorbing pistons are precisely checked for size to make sure they perfectly fit the suspension system. First, the technician needs to carefully assemble the housing. He tightly torques down the end retainer and applies heavy oil to the gaskets that form the seal around the chrome-plated steel piston. It's all about keeping the suspension sealed tight so the smooth chrome can slide freely without losing pressure.
When a moving part goes by a gasket, the gasket does most of the sealing around that part, but the last micron between the seal and between the part is normally filled with a very thin sheet of oil. That actually does the final seal.
If the chrome has been applied to the correct thickness, there is less than 1/1000th of an inch difference between the interior diameter of the suspension housing and the circumference of the piston. The final step is testing. Technicians must make absolutely sure the chrome plating dimensions are perfect and no air can escape, even under 500 tons of weight. To test the system, the chrome-plated piston and suspension housing are bolted into a steel box, nicknamed the casket. This box is an important precautionary measure. 1,100 pounds per square inch of air pressure is injected into the suspension, and the casket keeps the 3,000-pound chrome-plated piston from firing out like a rocket. Next, searching for leaks, the casket is carefully lowered into a 500-gallon tank of water.
It has to stay under pressure for 20 minutes. If we have no bubbles, we have no troubles.
If bubbles are spotted rising to the surface, the chrome plating isn't thick enough and the suspension is not airtight. A leak like that would lead to pressure loss in the field and violent shaking that could damage the earth mover's frame, making it undrivable. But there are no bubbles here.
Everything's looking good.
These finished struts are now ready for action. A super low friction suspension system, able to take on the roughest terrain. All because of scientists like Colin Fink and Chromium. From the mammoth suspension to the mineral oil lubricated wet brakes. Earth movers not only need to haul 320 tons of rock, they also need to stop fast. Brakes rely on friction to reduce speed. But friction produces a problem: heat. In a strange twist, the hunt for whales would provide the solution to keeping these powerful brakes cool: mineral oil. (1853). America is on the hunt for whales. 8,000 will be slaughtered in this year alone. The whaling frenzy inspires imaginations and books, including Herman Melville's Moby Dick. What they're all after is whale oil. It's extracted from the whale's blubber, or head cavity, and is sought after throughout the world for fuel in lamps. It burns bright, but as demand increases and the number of whales decreases, the price skyrockets. At the same time, across the globe in Lwów, Poland, a pharmacist named Ignacy Łukasiewicz is testing out his newest invention at a local hospital. It's a seemingly simple lamp, but it's been specially adapted to burn without whale oil and with an entirely new type of fuel distilled from petroleum. Its flame is bright enough to light a delicate surgical operation in the dead of night without any foul odor. It's the world's first lamp fueled by kerosene.
The benefit of kerosene over whale oil goes way beyond availability. It also has to do with shelf life. Kerosene lasts way longer, so you can store a lot of it.
Within months, word of this new lamp, fueled by kerosene, spreads around the world, and the hunger for its source, petroleum, takes off. The trick to finding more is finding a better way to extract it from the earth. 5 years later, Edwin Drake tries a technique used for drilling salt water. He erects a 30-foot derrick in Titusville, Pennsylvania. No one has used this method before. Most believe there are no large underground reservoirs of oil. But in August of 1859, he hits a huge pocket of black crude, and the oil race is on. Then, a critical event paves the way for the discovery of yet another petroleum byproduct: mineral oil. In 1863, J.D. Rockefeller joins the oil game. His initial interest is refining the crude oil into the already popular kerosene. But he quickly sees more potential. His competitors are distilling kerosene and dumping what remains as waste. Rockefeller believes there's more to crude oil than lamp fuel. His company, Standard Oil, goes to work researching and developing hundreds of useful new byproducts, ranging from synthetic beeswax to medicinal petroleum jelly, and a multi-purpose industrial lubricant. A lubricant not made from animal fat, like many lubricants of the day, but brought up from the earth, and therefore called mineral oil.
This can't be overstated. The push to get oil out of the ground opened doors to all sorts of technology. Extracting gasoline from petroleum was the basis for moving forward with the internal combustion engine.
Today, the process of separating mineral oil from raw crude is called fractional distillation. Each element of crude oil evaporates at a different boiling point. By heating crude oil to 650 degrees Fahrenheit, workers isolate the mineral oil by turning it into vapor. When the vapor cools, it condenses back into a liquid state for collection. Once separated, the mineral oil's thickness can be tested and adjusted.
Mineral oils from different parts of the world have different thicknesses or viscosity, and this is due to the molecule chains. Long molecules are more viscous, short molecules are less viscous. This is the single most important parameter of an oil. To keep the brake system cool, you need the perfect balance of viscosity. Too viscous, and it gums the system up. Too thin, and it doesn't stay between the parts.
The final product is ideally suited for each job and industry, perfectly prepared for the demands of this earth mover's brake system. At the assembly plant, a team of technicians puts together and tests the truck's muscular mineral oil-based wet brake system. In assembly, each brake needs 10 textured friction discs and 9 flat-surfaced separator plates. The friction discs have teeth on the inside that lock into the wheel itself. The separator plates have teeth on the outer edge that connect to the housing. The grooves on the textured discs look like the crosshatch pattern of a metal file, but the grooves aren't there to increase friction. Instead, these channels fill with oil, creating a slippery film. When pressure pushes these 47-inch discs together, the film creates an oil barrier between the discs, protecting them from wear.
Because of this oily coat, the brake discs never physically touch, and this is incredibly important for wear because it reduces friction, it reduces abrasion, and it reduces heat so that the parts last longer.
Since the system relies so heavily on mineral oil, the wet brake must be completely leak-proof. If any oil escapes the housing, dangerous friction can cause the unit to fail under intense heat, undermining the value of J.D. Rockefeller's discovery.
We'll put the bolts in, get them torqued down, and once the piston housing goes on, then it's completed.
In order to make sure they work properly, each brake gets a trial run on the test wheel. A technician attaches hoses that pump in the mineral oil-based brake fluid the same way it will function in daily operation.
What it does is cycle the oil through the brake for coolant, and then we run the coolant through the brake, and then we flush the system also for quality in the field.
First, he checks the slowing function of the brake. He applies just enough pressure to bring the discs together, not to actually stop the wheel from moving. The amount of rotational force is so great, applying full pressure on the brake would actually rip the test wheel out of the ground.
That's going to show us that the brake pressure is that we're applying the brake instead of stop, and then it'll hold, so we know that the brake works correctly.
The The slowing test is a success. Next, he runs a test to ensure the mineral oil's doing its job, keeping the heat down while the truck is moving. He turns up the speed of the wheel. The brake spins for 60 minutes while he checks the temperature of the oil to ensure it stays within limits. An undiscovered failure at this stage could lead to a much more significant failure at the mine site. With the test complete, everything checks out. A perfectly functioning wet brake assembly, ready to stop 550 tons while keeping its cool. An impossible feat without innovators like Ignacy Łukasiewicz, J.D. Rockefeller, and mineral oil. Brakes make this mining truck stop, and a powerful battery makes it start. Earth movers need to haul more than 500,000 pounds up steep grades, nearly 24 hours a day, 365 days a year, in all kinds of weather. It takes incredible durability and power from a 10-ton engine that delivers 2,700 horsepower. But it couldn't even start without a serious battery, and that takes the special ingredient sulfuric acid. 1781, University of Bologna, Italy. While experimenting with a frog in his lab, biologist Luigi Galvani makes a shocking discovery. He attaches a copper wire to the animal's nerves and touches its body with an iron probe. The frog's leg suddenly springs to life. Galvani thinks the frog's body is generating electricity. His colleague, Alessandro Volta, experiments further. Volta proves that the frog's muscles are not the source, but a conduit. They're passing the electrical current from one metal to the other, and it's all about electrolytes.
Electrolytes are mixtures like salt and water. They contain positively charged atoms called ions. And when those ions move from one metal to another, they create an electrical current.
Almost 100 years later, French physicist Gaston Planté is creating the first lead-acid battery. He uses a series of compact lead and lead oxide plates suspended in a powerful electrolyte. His electrolyte of choice? Sulfuric acid.
Sulfuric acid is a great electrolyte because it has a high density of ions, which means that it can move more charge from one metal to another. In fact, sulfuric acid is 4 times more conductive than salt water.
Though the sulfur in sulfuric acid is still mined in some parts of the world, today, sulfur is mostly created as a byproduct of petroleum refining. At petrochemical plants like this, sulfur is burned, enriched with oxygen, and then combined with already concentrated acid to create high-strength sulfuric acid. And then, based on the need, it's diluted with water to achieve the necessary final strength. And the modern 12-volt lead-acid battery? Well, its design is very similar to the one Gaston Planté made 100 years ago. There are 6 2-volt cells, and each cell has a positively and negatively charged plate. They're all submerged in our essential electrolyte, sulfuric acid. And when they're ignited, they create the ideal charge that gets our massive earth mover going. Back at the assembly plant, sulfuric acid batteries are the only way to start the 930E's power plant engine. It's massive and has a surprising configuration. There's both a traditional diesel engine and an electric generator. This diesel-electric power module produces enough energy to run over 1,400 households.
The crankshaft creates motion that transmits into the generator, and then that creates the electricity that actually makes the truck move.
When you're trying to move thousands of pounds of material, a diesel-electric motor is perfect. First, it has an incredible amount of torque, or rotational force, that comes very quickly. Also, between the motor and the wheels, there's very few moving parts, which means less breakage and a lighter carriage.
It takes 4 12-volt batteries connected in pairs. each pair producing 24 volts to fire it up. Building and testing this engine, generator, and battery combo is a huge undertaking that begins with pre-assembling nearly the entire truck at the factory prior to shipping.
How we looking, Mike? There we go.
Out on the mine site, it'll stand up to continuous abuse. But here, they use considerably more caution. Carefully marrying the massive diesel engine to the huge electric powerhouse, moving it foot by foot, the operator uses a waist-mounted control box to maneuver the overhead crane, checking alignment at each step before inching further.
How you looking, Sean? Coming down.
Finally, to finish the job, a technician bolts the vital, life-giving lead sulfuric acid battery box onto the front bumper. It's charged and ready to pump a massive burst of energy, 4 times more than an average car battery. A charge that would have been inconceivable to Gaston Plante when he first pioneered this battery.
Because of the electrolyte sulfuric acid, even a regular 12-volt car battery can have up to 400 cold cranking amps. That's more than an arc welder. This battery has more than 4 times that much strength.
Now, it's time for the main event, firing it up and making sure everything's running properly. This factory inspector has the honors.
You ready to go?
Yeah, we're ready to go.
He turns the ignition key to spark sulfuric acid's electrochemical reaction inside the battery, starting up this monster machine for the first time.
Open up just a little bit more, please.
It takes 2 mechanics and an electrician to run through an exhaustive list of checks, from precise engine operation to perfect hydraulic pressure and fully functioning lights and gauges. Minor problems lead to minor adjustments.
All right, just a hair up, Darren. We're just right, almost there. A little bit more. A little bit more. Bingo, right there, we're on it.
More critical failures could force the factory to disassemble the truck for time-consuming fixes.
We fire the truck up, we run it through what they call bypass. We do system checks, make sure there's no problems with the truck. And we just set all the pressure so when they get the unit to the field that it's ready to go.
When the final test is complete and everything checks out, the amazing Komatsu power plant is ever ready to deliver under the toughest conditions anywhere in the world. All because of Luigi Galvani, a frog, and powerful batteries filled with the electricity superhighway, sulfuric acid. "1,600 hours of hands-on construction have turned 5 powerful raw materials into the essential parts for an epic mining truck. Now, it's time to put it all together. But surprisingly, that doesn't happen at the factory. It could be done, but how would you get the huge final product to the work site? This giant earth mover is way too big for any road or any railroad.
To fully assemble them means that we could never ship them anywhere. The roadways and even the railways are not wide enough, if they are tall enough, to accept a full chassis assembled. They go in 4 or 5 major pieces. This is the most common way we ship our product for export.
The only choice is to have all the components, including the 6 giant earth mover tires, meet just in time for final assembly at the site, wherever it is.
As they arrive on the mine site, then, the Komatsu distribution network is in charge of assembling the machine back up into working order. The logistics of getting everything together and putting one of these machines together is very impressive.
And you won't find an assembly warehouse or hangar bay out here. There's no massive lifting equipment either. The final assembly team simply makes do, and all at the mercy of the elements. It's a monumental task, starting with the engine frame build, followed by the rear wheel motors, all the way to attaching the dump body. It takes 2 full weeks for technicians to build this beast from the ground up. Finally, the Komatsu 930E is complete, ready to take on the mine and get busy. Sulfuric acid goes to work inside the battery, kicking the power module into high gear. Building up speed, latex-based rubber tires grip the ground, driving the giant truck forward. Smooth, chromium-plated pistons inside the suspension absorb every rock in the road. Arriving at the end of the haul road, mineral oil-based brake fluid keeps the brakes cool while they bring the monster earth mover to a stop. And a coal-strengthened chassis stands firm under the weight of a 320-ton load.
What's amazing about this is that humans through the years have tried, sometimes failing, to make grand things. And here's a perfect example of us taking something raw out of the ground, extracting something from it, building something, then using that to go back and get more of the raw material.
From natural elements to the toughest dump truck on the planet. Built from raw to ready.